a real pleasure to introduce to the next speaker, Marc Vinot, with a background in biological and industrial processes, is in charge of biological processes at Urbaser SA, and has 25 years experience in the waste management sector. He began his career at Valorga in the field of anaerobic digestion. He has worked in Belgium, France, and finally Spain at Urbaser for the last 19 years. Over the last 15 years, he has worked mainly on all aspects of air treatment, anaerobic digestion, and composting. He has been involved in the design, engineering, and commissioning of large installations built in France and in Spain. Okay.
Okay.
Marc?
Hello.
Hello.
Yeah, you hear me? Okay,
yes.
Great. It's working. Okay. Thanks, Gloria, for the introduction. Thanks for the organization of the webinar for inviting us to present. And I will try to make up some time. It's not so easy. The title of my presentation is Environmental Challenges of MBT Plants, VOCs, Unpleasant Odors, and Energy Consumption. I'm going to talk about the challenges we face in terms of odors in the municipal waste treatment facilities, the VOCs and the different type of concentration of VOCs we got in the different areas of the facility. And I will speak about how to reduce the operating cost of ventilation systems in industrial facilities, in our facilities. Okay.
Marc, if you are moving your slides, we don't see them.
No, not yet. Now. Okay?
Yes, okay.
Okay. So, unpleasant odor, when you start talking about municipal waste treatment plants, the word smells immediately comes to people's minds. I remember a few years ago, 10 years ago, I arranged a visit from a facility for my children's class, and 10 years later, all the teachers and accompanying adults are limited. Their memories are limited to smell. So this for the population, this is the main issue or thought they got about municipal waste treatment plants is the smell, the odors. Okay, so odors is a sensation, as you all know, the stimulation of sensory cells due to gas phase chemical compounds usually found in very small quantity below the threshold of analytical detection, but produce a response to our olfactory bulb, and we got this sensation of odors. The main odorant compounds, if we want to classify by the main groups, we got the sulfur compounds, H2S, mercaptans, thiol, sulfide, and polysulfide. So the azocomposites, ammonia and amines, aldehydes, ketones, organic acids, terpenes, alcohol, aromatics, aliphatic, and this is the main. There is more, but this is the main ones we got in when we speak about odor compounds. In waste treatment facilities, the main odor sources are the nitrogen compounds that originating from the decomposition of nitrogen compounds present in the waste. The compounds we got is ammonia, the urine smell, amines, fishy smell, the sulfur compounds from the anaerobic decomposition of the organic fraction. We got hydrogen sulfides, this rotten oak smell, methyl mercaptans, rotten onion smell, dimethyl sulfide, this cabbage smell, and dimethyl disulfide. This is also cabbage smell, mainly. Not working. Yes, no. We got also nitrogenous organic compounds originating during the decomposition of proteins and amino acids we get in the organic residues or in the food waste, and the VOCs. For example, in aerobic and anaerobic decomposition process of organic material, we have a very high production of VOCs that contain carbon and are volatile at room temperature. So we got the alcohol, aldehyde, ketones, esters, the terpenes, and volatile fatty acids. So here we got a table of some chemicals with the odor threshold in ppm and the characteristics odor sensation we got with all these chemicals. Okay. Now, if we focus on municipal waste treatment plant, we have some areas where we have a higher generation of odors. Okay, the first building or unit where we get this generation of odors is the reception and storage pit. Because when we get waste, especially waste with high content of biodegradable material, it's prone to decomposition and odor generation. The pit can be around 2 to 3 day capacity of storage. So we get the material in this pit during a lot of time. And depending on the country, the frequency of collection of the waste in the house is quite different. For example, for bio-waste in Essex, it's nearly 1 a week. So when the waste is coming to the facility, it has spent 1 week in a container. So depending on these two things, we can have a very high emission of VOCs and other compounds. Afterwards, we get the pretreatment and the initial sorting of waste, the shredding and circulation of waste through the facility to segregate materials, also release gases and particles that generate odors. After we have all the package of the biological treatment, okay, to process composting and anaerobic digestion of the organic fraction of the waste. So this is generate volatile organic compounds and also odoriferous compounds. So we got here's the main units where we got this generation of other compounds. And if we focus on VOCs, there is a very close relationship between odors and VOCs. We all know this. These are diverse VOCs are a diverse mixture of chemicals that can range in odor from sweet to rancid. And these compounds are released during the decomposition of organic material, as I said before. And in waste treatment facilities, the VOCs are released by the anaerobic decomposition of organic waste without oxygen, anaerobic digestion, such as landfill and fermentation in digesters and putrefaction processes, the evaporation of solvent and chemicals in industrial or domestic waste, thermal processes, when we get inefficient incineration, you can have a very high concentration of VOCs at the output, and the composting processes, especially if it's not well controlled, there is lack of oxygen, excess of moisture, etc. And even if you are controlling quite well in a composting process, there is always, in a composting tunnel, there is always some area, some zone of the tunnels or of a reactor with a lack of oxygen. So with, let's say, some points of anaerobic decomposition in the composting process, it's occur a lot. We get some example of common VOCs in municipal waste. So this is very general. The methane, which is odorless, and butyric acid, propionic acid, aldehydes, and terpene. But if we go in the different areas I mentioned before, for example, reception building. Sorry, the tables and graphics are in Spanish. In the reception building and storage pit at the end, we see that we have curves between 13 and 11 ppm in curves, which in odours we are about 6 to 2.2 thousand odours units. And if we look at the main groups of curves we got in this part, it's aromatic hydrocarbons, ketones. After we got some terpenes, some alcohol a little bit, and aliphatic hydrocarbons, organic acids, esters, and some halogenated compounds. Okay, and we see for example, during 48 hours, we can see when we have some peaks due to a very high quantity of trucks coming in this area. If we go to the pretreatment building, so here we can see that we got the curves quite high, between 31 or 4, nearly 5 ppm, depending on the hour in the day. It means depending on the how it's working, and between 12.3 thousand to 900 odor units per cubic meter. And the main families are the same as the one we got in a reception area. Okay. If we go to specific equipment in pretreatment, so it's quite different. If we go to a ballistic separator, for example, we are about 22 ppm of COV, but in odor it's only 3.5 thousand odor unit. In a refuse press, the quantities are lower in terms of VOCs, between 3 to 10 ppm, and 400 to 2,000 odor units, depending on the moment in the day. Okay, and in terms of family, it's the same. We got the same main families, but we start to have in some equipment aldehydes that we got in the top of the columns of each equipment. If we go to a composting unit, so here we are in a composting building. So we got VOCs around 17 to 7, depending on the moment of the day, and between 6 to 3,000 odor units. And it occurs the same in terms of the families of VOCs. We are with the same families, with some aldehydes at the end, esters and aldehydes in the composition of the VOCs. So as somebody before speak about the limits, we have to comply with some limits in terms of emission, the total VOC. So it's indicated in the decision of the EU in the 2018/1147. Okay, so the BAT. And if we go, there is a definition of VOC based on an article of the directive 2010/75, and in the BAT 34, it explains the different technologies to reduce the emission dust, organic compounds and odorous compounds, including H2S and NH3. And in this same BAT, there is some associated emission level that have been mentioned before at the beginning of the webinar for the total VOC between 5 and 40 milligram per normal cubic meter. Obviously 5, it must be with a TO, that's clear. But the value of 40, it's normally the limit that is asked to comply. And when we go to way to make the measurement, the control of this parameter. It's indicated in the BAT 8. It's the directive 12.6.19, which indicates that when this is the Spanish version, but we have to use a flame ionization. And what happened at the end? We are speaking about odours because, as we see, one of the limitation is total VOC and odor concentration. We are speaking about odours. We have the dust, H2S, and H3. Well, there is no limit for H2S, but in H3 in the BAT. But we are making the measurement of total VOC with flame ionization. So it means that the methane, which is odorless, will be included in the measurement of total VOC. And as I said, in the reception area, the storage pits, or in the composting phase, and obviously in anaerobic digestion building when we get dehydration of the digestate, the output material of a digester, at the end there is some methane, and it means that when we get the limitation only on total VOC, it includes the methane. So actually, there is some facilities where it's quite hard to comply with some values when they are not asking for 40 milligrams per cubic meter, but for 30 milligrams, and the value of methane is making that it's quite hard to comply with the limits they are asking when they are asking for a very low limit. If you have a biological treatment, or well, if you don't have a thermal oxidation.
1 minute, Marc.
Okay, in some countries they are starting to speak about non-methanic VOC to avoid to have methane, but there is not a measurement procedure existing. The major cost of managing the odor problem in a facility is energy consumption. This is the challenge. So how to ensure acceptable condition in a municipal waste treatment building, increasing the air change per hour. It's a lot of money because it's a lot of flow. So this is not an issue. In the past, the grid of aspiration of piping was more like you can see in this picture of a drawing, but it's a lot of pressure drops. In this picture, it's nearly pink, but you can see this type of concept of ventilation. Also, some aspiration point in some equipments, but it's a lot of pressure drops. So we have to think that we got some ways the process, the equipment. There is natural convection, and we have the air with the odorous compounds. That is there is a convection to the upper part of the building. So with the normal louvers of normal concept, usual concept, at the end we have stagnant air, which creates some problems, because with humidity you can have rain effect in the buildings that can eventually create corrosion in the wall and roof building, and we can see it in this upper part over there above pulper in a facility. So this is an important issue. Okay. That shows that in Urbacea, one of our main objectives is decarbonization, and we're doing this. One of the ways is to reduce electrical consumption in all the ventilation systems. So what I explained, we have the waste composting and the stagnant air, because the extraction can't have an impact on more than some, let's say 1 meter in the best case. So what our concept is to create a dynamic zone using transfer fans to push the air near the grid and near the extraction pipe to reduce the quantity of piping, the length of the piping, and the pressure drops. Okay, so because those fans are only 0.3 kilowatt each fan, and there has an air supply range of about 20 to 30 meters, so they can push the air and transfer the air, contaminated air, near the grid. So this is the concept we developed with a company. Okay, and to check this, we carried out a fluid dynamic CFD study. Okay, to check the design. We mainly focus on temperature, velocity, and LMA. The local mean age, it means the air age, the time required to supply air to reach a point in space from a supply inlet. Okay, so for example, we have on the left the actual state, the old state, let's say, and with the new design, the change in temperature. So we were able to reduce 5 and more than 5 degrees the temperature in the building. In that case, it's at 0.5 meter high, and at 6 meter we got the same impact. So the conditions are better in terms of temperature. We move the air, and in terms of LMA, age of the air, we can reduce more than 50% the retention time, and to avoid stagnant air and some problems you can have in some buildings. Okay, and well, circular economy challenges and R&D. So we got new developments in environmental technologies at the Alfonso Mayo Basser Technological Innovation Center, and we work a lot in all the ventilation and air treatment issues. And you get my emails if you have some additional questions.
Thank you, Marc.
With the support of the European Union's LIFE program,